Welcome back, and let's look at stress resultants, part 2. Where I want to talk now about, where I want to specifically now talk about what other things we can compute on the face typically. So let's imagine now some kind of a face, and in the middle of this face, let's have our local coordinate system. Yo, what the hell is that? Apologies for that. So let's call it X, Y, and Z, for instance. Okay, so that is maybe a description of just a system that I have. And on this face, we have essentially an area associated with a normal. And this face, the normal is then in X, for instance. Okay, so that is now our face normal that we have. And then on this face, there's an arbitrary traction that's associated with NX. Okay, so the question is, what happens? So what I'm going to do is, instead of just making it NX, let's leave it as NX, because we are going to be we're talking about shear in the X and Y, and normal in the shear in the Y and Z, and X in the normal. Okay, so let's just first think about what are all the things that can happen on here. So we've already looked at the normal. So we could say we could compute f of x, the normal. We could maybe think about computing a shear force. So there's a f of y, okay, and there's a fz, which is the shear in that direction, a fz. Okay, so those are the three things that we could think about. So we've tackled this already, okay, and the way we tackled that was by saying, let's integrate, just as a part of a recap, integrate over the normal x, area at normal x, of the traction, okay, the tractions x component over dy dz. That is what we said there. If I now want to say, let's do the force in the y, the shear, I can say let's integrate a nx ty component nx dy dz. Okay, and again the ty component is of the traction vector. If I go from the stress components only, which is the stress vector, stress tensor that lives in the space, if I evaluate it at the x associated with this face, x at a, for instance, nx, then I can plug in that value and then have the stress at that face only, and then I can say, fantastic, dot this with the normal, and then I recover this. Okay, but just bear in mind, when I write these down, it implies we have evaluated the stress tensor at this face and dotted it with the normal associated with this face, and then I recover this traction vector on that face. Okay, and then fz is again an x t z component. So these are the two shears on that face. What remains? Okay, so what can happen in this face? So if you want to think about bending, it's pulling and pushing on that face. Bending is a pulling and pushing exercise on that face. So if we're doing pushing and pulling on that face, I can then say we can be pushing, pulling around this axis. So I can think about bending in the z direction. Make sure I'm still on the board. And I could say I could be pushing, pulling around this direction. Okay, so that is essentially then around the y direction. Okay, y-axis. Sorry, that is essentially what I could do. And so if I do this, I can say, well, let's think about it. If I want to do pushing and pulling around the z-axis, so it's bending around this axis, yeah, I'm looking at the x component. So the integral of the face area is not going to change. I'm going to be looking at the x component of the traction vector multiplied by the arm, y, before I integrate. First I have to ask myself, what is the sign? So if let's say I am pushing this side, so let's say I'm pulling this side, so my traction, because the traction vector is expressed in this global coordinate system, the traction has got a positive value and the distance is a positive value. So if I'm doing this, if my force is in this direction and my y is in the positive direction, I am essentially applying a bending moment, okay? But this will make this thing go like this. With me? And so that is a negative bending moment, it should be. So I need to put a negative in there because it's sort of this kind of curvature. So if I had this kind of curvature, I would like to see compression at the top. So I would like to push inside. That's a negative traction. Multiplied by positive y, that's a negative then. And so this negative then will make it a positive if I go that direction. So this all works out fine. Okay, and then I can follow the same argument and say, what is my? For my, I can essentially go and say, it's the pushing and pulling like this out of this plane, and I can derive the expression for my. Okay, so my would be something like, let's look at the sign. So ny would still be nx, but it would be then essentially in the z direction, the z arm. So if my nx is here, and I'm in the z arm, z direction, integrate over dy dz. Okay, and again, depending on what kind of notation, but typically this would what we recover for the mz. Okay. And then the last thing it stays, what is the last thing that we still have? So we have 3 forces acting on the face, the normal and 2 shears, 2 bendings. There's still something missing. What is the 6th thing? It should be the torque. Okay, so essentially the torque would be given by what? It would be this kind of around this x-axis. So I've got stuff in the plane. What are the things that would contribute? Well, it's essentially all the shears on that plane. So this shear in the z direction with its moment arm y. So in the shear in the z direction with its moment arm in the y. And then the shear in the y direction with its moment arm z. Shear in the y direction and its moment arm z. Okay. Integrate it over the area normal x. Integrated area, call it dy dz. And there's also, let's just call it dy dz to make that clear. The question is it positive plus? Let's look at the signs. So if I think of this y positive and the z positive, I am getting something that goes like this. So I've got something that goes into the page. If I think about my z being positive and my y arm being positive, I get something out of the page. So depending on how I want to define it, but essentially I would get a difference in the direction between those two. So it needs to be something minus something else, or minus plus, if depending on what kind of notation you want to use for positive, inside, or out of the page, or left or right rule, whatever. But the bottom line is this is what we have, and here we have now our torque as our 6th component. So we can compute 3 forces, 1 normal, 2 shears, 2 bending moments, and 1 torque that's acting on that face, and that counts for every face. So these 6 things you must be able to compute with comfort. And this is something I think you've done in other courses. You should have done this in MOW227, just briefly, and MSY310 quite extensively. But if not, please make sure you go and recap those material that you've done there. But let's make sure that we visit these things in a good spirit, because in the end, this is the way we go from a displacement field towards the tractions that are applied. And what we are doing is we're going to be checking. Okay, so I just want to maybe highlight this point here. This allows us, to check whether a displacement field that we are given, is related to tractions at a surface. How it's related to a traction at a surface. And typically what we have is, if you give me the displacement field, I can compute the strain. I can go and compute the stress tensor, okay? Now I have the full stress field for that problem. Now I need to go and check, does this stress field that are given to me, that I can convert towards tractions and stuff, and I go and compute my macroscopic moments and forces on a surface, does it make sense based on the problem that was stated? Okay, so if I give you the displacement field, I can't give you the tractions independently. It's already incorporated. All I can do is check whether the displacement fields, tractions that I derive on those surfaces and those macroscopic force, like shear and normal forces and bending moments and torques, those things that are derived for those phases, if they are consistent with what is claimed to be have applied by, in the problem. And that is important that we were able to do that. And similarly, when I do a finite element method later on, we're going to be doing FEM, apply stuff, and we're going to get a stress field out. So we're going to get a displacement solution. And FEM will allow us to see the stress field. But I can then take that stress field and say, let's go and check whether that's finite element stress field. Yeah? What are the attractions? And what are the microscopic stress resultants that follow on those surfaces? And are they what I expected them to be? Are they what I wanted them to be? And that's the cool thing that we can be able to do now, is that we can go from macroscopic forces to a stress tensor, and then we can go back from the stress tensor to the macroscopic forces. So this completes the check. All right, and then the next lecture, I'm going to quickly talk again about why all of this was important, why all of this stuff with stress tensor is so critical, why we couldn't have just done it with this, because this is an important point to really appreciate and understand. Thank you.